Damn.
Yeah. It's like, show of hands, how's everybody's midterm week going? Like this, like chilling, terrible, middle?
It's okay, I'm standing out of here right now.
Alright, yeah. Right after this lecture, we are going to go study for, well, she has 3 midterms like this week, tomorrow and the next day. I just have 1, so I'm kind of chilling. Alright, I hope everybody's got, come on, Parth.
It's not opening.
Wait,
Okay,
really?
then just save the link and then you can put
Like,
it on later.
I'm just like spamming sign in.
Oh,
It's just not letting me sign in. It's fine.
Oh, alright. If you have the link, try it again later. Yeah. Alright. Wait, this thing isn't on.
There we
Okay.
go. And yeah, today's overview, we're going to talk about PID. A lot of you guys will be like, what does this acronym even mean? Don't worry, we'll talk about that. And we're just going to talk about how it's applied in Micromouse and just in terms of distance control and angle control. And then we're just also going to go briefly on the implementation of it.
Yeah, so like after today's lecture, like you'll be able to like tell the rat like, oh, I want to move this set amount of distance, or I want to turn like this set amount of degrees. And this is just like the algorithms, like the control algorithms that we use to implement that in code. Right?
And yeah, so PID is a control system. It is one of the control systems out there, and that's the one we'll be using in the project. It uses a sensor feedback to regulate the output of the system to reach some goal. And for Micromouse, it's like our sensors are IR and encoders. They just kind of read in like the surroundings and like what your current position is. Our outputs are left and right motor speeds. And our target is to drive through a maze without running into the walls. Or maybe run into the walls. We can figure that out later. And so PID is a feedback loop. It's a magic box that controls the mouse's movement based off of what it sees of the sensors. And it also, like, whatever it outputs, it's also get fed back into the loop for like further calculations and all that, hence feedback loop.
Okay, so yeah, it's not actually a magic box. So PID, it stands for proportional, integral, and derivative. And alright, so before we talk about like what each of these blocks do, I'm just gonna describe this. You probably haven't seen like a diagram like this before, maybe you have, but it's like I believe they use these diagrams like most control systems. So you have your desired state, E of t. That's like so say like my goal right now is to walk towards Megan, and then we have an error state on the next slide. Before I do that, so the goal is to change our output so that the error becomes as little as possible. It's like the error between us would be like what, 15 feet? So the goal of this system would be to walk towards her and decrease that amount of error. And that's the main gist of what we're trying to do. So if we go more in depth, this just talks about like the error. So in code, we will measure like from our encoders like what our current error state is, like how far away we are from the goal. And then that, you can see that error term is passed to each of these 3 subblocks. And what those are, we noticed like each of these it has a KP, a KI, and KD. Those are constants that we experimentally determine. And we're gonna go through like what we're looking at here. So KP, just remember all the K's are constants. KP times ET. So that just means like the farther away I am from the goal, I'm just gonna multiply that by some constant, and then that's gonna be sent to the control signals. Like I'm 15 feet away, let's just say like my constant's like 2. It's gonna multiply that to be like an arbitrary value of 30. We're gonna add 30 to our control signal. And then so that's just like the farther away I am from the goal, the bigger that term will be. So here I really want to like walk towards her, and yeah, that error term will be huge, but here it will be less the closer I get to her. And then when I get to her standing in the exact same spot, this term will equal 0 because the error term will be 0. And then next up we have Ki. This is like, actually I'm gonna do KD first. It'll make more sense. So for KD, it's like, notice instead of just straight up being a proportional constant here, KD is multiplied by the derivative of the error term. And that just means like, if I'm walking towards her, that means the error term is going down. So then this derivative will be a negative, and then this would subtract from our control signal. So then we're gonna get more into like what that does and why we want that later on, but like, just know that this is what we mean by proportional, and this is what we mean by derivative. It's like, yeah, in terms of how the error changes. And then integral, that would be like the integral of the error over time. It's like, if Megan is like walking in the same direction as me, as I'm going here, then these two values have things, but this one, the error stays the same, but our integral, like if our error stays a constant, then the integral would like grow and grow. It's like I'll know like, oh, I need to speed up. So it's like, for example, if I'm like trying to chase a car and the car is like going at the same speed as me, I would know like, oh, I'm not actually making any progress. I need to speed up. I need to put more effort in. And that's what that integral term is. And then, and then all of these subcontrollers will be combined to just actually generate the speed for our motor. And don't worry if like you're confused about this at all. We're gonna give a visual representation here.
And so yeah, here's just like a little like GIF with like how the proportional and derivative terms come into action. So like without damping, like such as like the blue square on the very top, the system overshoots, and you can see it just oscillates between like our goal here, right? And then so like this is why we apply the damping term with like our derivative. But as you can see with the yellow case, actually too much damping is not the best for our system because it takes longer than it can. And you can see under damped cases where it's like it just goes past the goal and then it slowly goes back. That's still not optimal. With the red case, we have it perfectly where it's just it takes the minimum time and it just stops at the goal, right? And yeah, as you can see, the green one is just sitting there. The system won't do anything if there's no driving force. It's not going to change. It's just going to remain there.
Oh yeah, and then so a reminder that like when we talk about like driving term and damping term, we're talking about that's going to be the proportional and derivative subcontrollers. So like here, we don't have any like proportional derivative subcontroller here. Like KP is 0. That's why that's not moving. KP is 0.1, but then we have no derivative term. So what the derivative term actually does is like, it sees like, oh, we're getting towards the goal like really fast, so I'm gonna slow down so that like I actually stop at the goal. So that, for example, that would be like, oh, I'm running straight towards Megan, and then like once I get to her, if I'm still going full speed, I'm gonna overshoot, and then I gotta go back. And if I'm still going full speed, then I'm just gonna keep going back and forth. But what the derivative term lets us see is like, oh, I'm about to reach the goal, so I'm gonna slow down.
Like,
and then, yeah.
Like mathematically this makes sense. It's like when you think about it, your derivative it is like negative as like your distance between your like where you are and like where your target is. Your error is decreasing, so that feeds in a negative into our signal, so that dampens and just slows you down.
Yeah.
Did you have a question?
Have you guys taken physics 1B?
Yes.
Yes.
Is this the same as like driven oscillators?
Sort of.
Same idea, yeah.
Same idea. It's probably similar math-wise.
Like,
Would it be possible to like calculate the ideal values to reach critical depth, or do you
Like it's more like because of the nature of our motors and how it varies with battery as well. Like it's probably better to experimentally determine. Like there's gonna be like a range where you can like fine tune it, but like again with just it's a physical system and also the maze isn't like exactly the same throughout. As like the best we try to keep the surface even. There's gonna be some like oddities, so you'll just have to experimentally determine that.
Yeah, so since it's real life, it's a lot harder than just the equations. But you are right in that like, if you remember like the damped oscillation, like the shape of that graph, it would be like this and then like go like this kind of.
Yeah.
That's the same thing as that. So yeah. Is everybody following so far? I know it's like kind of a lot. Yeah.
Are the constants like KP and KD set by like whoever's coding the program?
Yeah.
Yes.
So in assignment 3, you will be like testing out what different constants do and like what the goal is to just like get it like the red movement here, where like if I run towards Megan,
And then
I
just
stop.
perfectly after
Yeah.
the goal. That's our goal. It's like it just takes a bit of time and just experimenting to find out what works the best for you guys.
Yeah. Okay.
And also just a quick aside, it changes with your speed. So yeah, you can figure that out in the assignment later.
Any other questions so far? All right. Cool.
All right, let's go. So this is just more on like derivative.
Oh.
So yeah, you can see how like the shortest time without overshooting, that would be the red case there. It's what we call critically damped. We actually have a terminology for this. It's basically, it minimizes the time. It doesn't take too long to reach the goal. Neither does it overshoot. And it just stops perfectly on the goal. So you guys will be trying to reach critically damped in your cases.
Oh yeah, so you may have noticed in this previous slide, we're only showing the proportional and derivative term, and that's just the P and the D, but where's the I? So we don't for our case, we don't actually need the I. If you remember the example I was talking about, like, we use the I when, like, if Megan's, like, running away from me as I'm running towards her. So yeah, but, like, in our case, we know exactly, like, what distance we wanna run, so, like, that won't change, like, between, like, the time we get there and the time we reach it. So, so yeah, that would be called steady state errors, like, if we're both, or if I'm running towards her, but, like, the error is not going down. And then, yeah, Micromouse, the I term isn't useful for us, so we just don't need it. But this is an example of if we did need it, like, if we're chasing after something that's moving away from us, and our error terms, we have our P and our D, but no I, it would look like one of these top three, where, like, we're not actually keeping into account, we can't see, like, oh, this keeps running away from us, we're not making any real progress. But then when we add an I term here, it can actually see, like, oh, it's running away from me, we're not making progress, let me speed up a bit until I'm there. Okay. Oh yeah, and this is just what I said, in more words from when you guys look back on the slides if you want. And yeah, green is the only one with an I term. All of these other I terms are 0. So that's why it makes no effort to catch up.
And you.
Oh. Okay, sure. So yeah, in addition to that, like, we're talking about like just going forward at a set distance, but now we also use it in Micromouse to turn a set distance. So in this example, like, this is very bad. It has a damping term, but, like, we see, like, the critically damped one is this one, because it gets to it in the shortest amount of time. And that's how we find the error. Instead of the error being, like, the distance from the target, it would be the difference between the angle, the current angle, and the desired angle. And then on the mouse, like, you guys did encoders last time, that, like, measures, like, the wheel rotations. And we're actually going to be using those wheel rotations in this new assignment to tell, like, how far we've gone and how far we've turned. And then, yeah, so this is how we're actually going to implement it in code. Just like the output of our PID system, or our PD system, is just going to go, like, positive to one motor and subtract it from the other to make the mouse turn. Don't worry too much about that right now. You'll see what we mean in the code. But that just means, like, the PD controller outputs one control signal, and then it will make one motor turn more to the left and one motor turn more to the right.
Yes.
So, like, that would make, like, one motor
One turn
faster.
It's like, no, it's just more like, think of it as like turning in different directions, like that's how you kind of turn.
Yeah.
Does that
Like,
make sense?
Yeah, I
Like
was
one's
thinking,
going
like,
backwards and one's going forward,
yeah.
so you'll have to turn.
Yeah, I was thinking, like, maybe one goes slower than the other instead of slower.
That is-
Yeah, that also works.
That also works, I believe that's a more advanced way to turn.
Oh no, he just means like so when we're going straight, also in the code what we're gonna set up is like if we're going straight but then like we start to veer off a little bit, it'll notice that like, oh, one wheel is turning more than the other, so then it's gonna speed up the left wheel to get it back on track. It's like there, and then left wheel speeds up, and then it would just stay on track.
Yeah.
Does that answer your question?
Yeah.
Okay. Nice. Everybody else good? Alright, cool. Oh, is this my slide? Okay, so yeah, this is what you're actually going to be doing. It's set to like a very slow minimum speed for just so we can prolong the video, to be honest. But yeah, so this is our, what the goal is for our distance controller. It will go we'll be able to tell it in code, like, oh, go this set distance. In code here, it's like, go 2 cells forward. And then, as we've said earlier, like, we can't just set the motors on for a set amount of time because, like, difference in the motor power levels, like, it would veer off, and then also it would go different distances based on battery charge. So yeah, that's the goal of the distance controller. We have it set to like 2 different PD controllers. One controls like how far we've gone if we're like trying to go forward, like how to calculate that error, and then on the other hand we have our PD angle controller. So that instead of looking at like how far you are from the goal, like distance wise, like how far you are from the goal angle. It's like what we were talking about earlier, like if we're here and the goal angle is here, we're gonna speed the left wheel up and decrease the speed for the right wheel, so we go like this. And then that, yeah, this pretty much sums it up. Okay. Right, let's see PID. Everybody's still good? Still following? Alright.
Alright, and so here's the actual mathematic equation to it. Like I know we like showed you the diagram of it earlier, but here is what it looks like in terms of just actual equations that might be more familiar than the diagram. So we defined earlier, like ET is our error function, basically how far you are away from your goal, whether it be your distance or like from your angle. And for each distance controller, for the distance controller, for example, the error would be the number of encoder counts to reach the desired distance minus the current encoder counts, which is like your current position versus where your end position is in a way. And derivative can be calculated uses the previous error value subtracted by the current error value. I'm assuming everyone here has like taken at least a little bit of calculus before, right? So we all know derivative is defined as like the change of a function over an infinitesimally small time. Well, to find the actual derivative, you would divide by elapsed time. I know I said previous error value minus current error value. It can be accounted for by the KD constant itself, and why this works is because we're on a constant clock speed, which is already accounting for like our change in time being constant, so that we don't have to, it doesn't vary with time. So we can just move that into the constant term instead of just leaving it with the error term, if that makes sense.
Yeah, and I also will add like the speed that we're running this like error function at, like the time difference between this and this, like the previous error value and the current error value is like really infinitesimal. It's just really small. So yeah, it's like a really good estimate of our change in the goal, in the error. Right.
And it's like, yeah, you will have to experimentally determine KP and KD. And since you guys have a distance controller and an angle controller, you'll have 2 sets of KP and KD to fine tune. And yeah, just a little bit of a thought experiment just to help you guys just kind of understand this more. So imagine we are a distance away from our goal. Here would be a positive error versus a negative error, and we're starting at rest. Can someone tell me what the error would be at this moment? Like if it's positive or negative or 0?
I think it would be positive.
Yeah.
Yeah.
Yeah, it was that simple. Yes.
Okay.
Yeah. So don't overthink it, guys. And like, what would the derivative be if we're stopping from rest? Starting from rest.
Okay. 0.
Yes. So yeah, we want to emphasize like, so at the start when you're starting at 0, it's like your error is not changing because you're not moving yet. And if your error is actually pretty big, like you will have a pretty big positive error because you're pretty far away from the goal. And yeah.
Yeah.
That's just reflected. That will be reflected on the output of your on your PD controller.
Yeah. So this KP term, that will be like pretty big because you have a big error value, big positive error value, and then the KD term, this part would be 0 because your derivative is 0 at the start because we're not moving. Okay. Then now.
And like now, as we're moving towards our goal, would someone like to answer if the error is still positive or negative or 0?
Positive but small.
Yeah.
Yeah.
And how about the derivative term?
Negative, I think.
So yeah, you can note that like our error term has gone from a big error on our previous slides to a smaller error now, and our derivative, because since we are decreasing our distance to the goal, it is negative. So it is rapidly approaching our goal and being dampened to slow down, to try to not overshoot. And now, in the case of overshoot, would someone like to tell me, like, how the error term is and how the derivative is? Yes.
The error term is negative and the derivative is plus. Wait, no, it's still, wait.
Yeah, keep in mind, it's still heading in this direction at this
Still
point in time.
negative, yeah.
So it's going from, like, that's just called zero error to negative error.
Yeah.
So that would be negative, right?
Yeah, and like again, like this change will still be reflected in like our P subcontroller and our derivative subcontroller. Just it mathematically works out.
Yeah, so now what we would have is like now that we have like small negative error, sorry, this term would be negative, and then also since we're still headed in this direction, the derivative is still negative, so both these terms are negative. Both of them are telling us, hey, we need to go back.
Yeah. And then like we're almost there, right? So right now we're going backwards. What's the error? What's the sign of the error and what's the sign of the derivative? Yep, you're right. So like since we're still like we've overshot the goal, the error is still negative. But since we are just heading backwards, like our change in our error is actually positive. So it's like one is negative, telling us to go backwards, and the other one's telling us to slow down as we're reaching our goal. And yay, we reached the goal now. So
Yeah, now that error is 0, KP should be 0, and KD should also be 0 after a set amount of time. So yeah, that makes sense to everybody? Right, cool. Oh yeah, so now we're actually going to talk about how we would implement it in code. So like, this is like what our output looks like, what we set our goal and errors to. So our goal, okay, so for the distance controller, this like determines like, it's the example like, oh, I'm trying to walk towards Megan. I have a set distance that I want to go, and we mark this in our code as encoder counts. Remember from our last lecture, we have like, I think 360 degrees per encoder count, or like, we can measure encoder counts in terms of degrees. It's like 360 encoder counts would be about like 1 rotation of the wheel. And then so we can set our goal in terms of distance, and then our error would just be our goal minus like our current encoder count. So we just like compare what our encoders are currently reading to the goal that we set, and then we put it through our PD controller, which you set up in the code with like the proportional values and then like the derivative terms. And then after it goes to that controller, we get like a single number that you would output to both motors. Like in assignment 2, you were able to like set like, oh, I want to set the duty cycle to like 0.5, 0.4. This will give you that value that you're gonna pass to the motors. And then on the other hand, we have our angle controller, and then this one is used to one, it's just turn like a set distance, a set rotation, but then also we will use it to drive straight. It's like we're gonna end up running both these controllers at the same time. So that like when we're trying to go forward using the distance controller, while that's running, we also have the angle controller running with the goal of being 0 degrees, so that anytime we like start to veer off, it will detect that and then bring us back on track. So then this works, the goal we set to be like a difference in encoder counts that will correspond to a certain angle. You will have to determine like what this difference will be experimentally, and then we determine like how far we are from the goal by just like having the difference between encoder counts. So we set the difference between encoder counts that we want, and then we compare it to our difference right now, and that will be how we determine how far we are from our goal. And then once we do this, this will output another motor, another number that we will, instead of adding it to both motors like we do for the distance controller, we will add it to one motor and subtract from the others. That way they turn in different directions. I know that was kind of a lot. Did that make sense to everybody? Okay, cool. And yeah, so just remember like we're gonna have both these controllers running at the same time, and then they will both like if we add both these outputs together, we'll get our desired speed for the left motor and the right motor that we can just directly tell the motors to spin at. And then yeah, this is just us reiterating that like if we want to drive forward, we run our angle controller with the goal distance of 0. And yeah. So now like this is just like some tips and strategies for when you're actually doing the assignments and like setting up the controllers. Oh yeah, so what I was talking about here is like you're gonna add the outputs of both of these. Like this is gonna be a single number, this is gonna be a single number, and then you're gonna add both of them, and then that's gonna be like your motor speed that you're gonna pass to the motors. It'll make more sense once you do the assignments, but just know that like that's how we combine the outputs of both controllers. Went over that. Oh yeah, so this is when you're actually experimentally determining the constants. You're gonna start with with a derivative term of 0, and then because you want to find the proportional term first. Remember, like when the proportional term is 0, you're just not gonna move at all, and the proportional term is your most important term. It will get you like most of the way there. The derivative term is just there to make you not overshoot. So you'll experiment first with like finding a good proportional value that works for you, and then once you're like slightly oscillating at the goal, but you get there, then you would start messing around with the derivative term. And then that's what I just said, like we start from Kp is 0, and then we slowly increase it until we get to the goal most of the time, and it just oscillates a little. And then we just add a little bit of dampening, and then that should be critically damped motion in theory. And then just some more stuff to worry about. Your motors would behave a little bit differently depending on the charge level. So you guys all have chargers in your kits. If you don't know how to use them, just ask one of us or like any of the officers in the lab. But yeah, so like we recommend just like every week you charge them, just that it's like at a consistent level of charge. It doesn't have to be like fully 100% charged. Maybe like 70% to 100% should be pretty consistent. And then also keep track of what constants you've tried. This will be like your KD and your KP, because like you could be like, oh, I have these constants and they seem to work like pretty well, but I'm gonna try these other constants, and then you try those other ones, it just works terribly. But then you already forgot what your original constants were, so you just want to keep track of like which constants work and like how well they worked. Okay, Maggie, you want to take the slide?
And yeah, so just to recap, PID is the control system we'll be working with, and it just controls the output of systems that attain a certain goal. In some cases, a PD or a PI system may make more sense, like you don't have to use all 2 subcontrollers. In Micromouse, we only use like the P and the D subcontrollers. KP and KD should be tuned in order to make your system critically damped so it reaches there at a minimum time without overshooting. And multiple controllers could be used simultaneously, like we are using our distance controller and angle controller at the same time. And yeah, so that just allows us to move precisely throughout the maze. Any questions?
Yes.
Why are ankle controllers like needed when you're moving straight?
Because it's just with the way how our motors are, and just like how the ground may be, how like the floor of the maze might be uneven, like your motors might be turning out at a different rate. So we just use an angle controller to make sure like you're still going straight. Like if you set a goal distance to 0 and like you deviate a little, you can just return back to like going straight.
Yeah.
If that makes sense.
So like a real life example, not me running towards Megan this time. It's so like if you're driving on a road, you're constantly like fidgeting with the wheel. It's like straighten yourself, right? It's like all the distance controller tells us like, oh, I'm this far away from the goal and I'm just going forward. It can't actually see like the angles and like how far we're veering off from like a straight path. That's what the angle controller does. So just imagine like angle controller is just like turning the wheel of a car. Distance controller just pressing the gas pedal.
Gotcha. Okay.
Yeah.
Thank you.
Yes.
I don't know how applicable this is, but how does the angle controller account for skid?
It does not. So what you would do to account for skid happens when you're like running it. I don't know what slide I'm going to. There's no slide for that.
Like skid happens like when you're like one thing it would be
Slide actually. Oh yeah, keep talking.
it's like when, to be honest, it's low key like when you have like too much to which speed it's not stopping in time. Like unfortunately we cannot, because of the way that we're tracking our position and our speed, we're tracking our position, it cannot be accounted for, which
Oh yeah.
well, like cannot be accounted for like without like additional sensors for the most part. So that
Okay.
will be something.
Yeah, so like the way you get skid, like the way we're doing it right now, it's yet going at a really slow speed, so there would probably be
skid.
little to no skid. But if you want to run it at higher speeds, what you would do is you would add an acceleration constant, so you're not changing speeds too rapidly, because skid only happens when you're accelerating or decelerating really fast. Does that answer your question?
So are additional sensors allowed in the normal or the Micromouse?
Well, the thing is, well, that's what we're going to be introducing in our next lectures. We actually have IR sensors on our mouse to just kind of help you see where things are.
Yeah, and then in addition to all the sensors that we'll eventually have on our rat kits, when you guys make your own mice in the winter, you'll be able to add whatever sensors you want, just like complete freedom, as long as we can actually buy it.
As long as we can actually buy them. It
And, you
mostly
know,
fits
not-
into
not
AMC
illegal.
rule. As long as like it mostly fits into like the Micromouse competition rules and it's like it's reasonably attainable, then we'll try to help you get it.
We do have budget set aside for you guys to order whatever parts you want, though. Okay,
It's a fun time.
while I'm doing this.
Yes.
And if,
Have people used gyros before?
yes.
We have tried with gyros.
So, what, oh man, I gotta go back. Okay, yeah, so how you would use gyros is, that would be how you get your goal in error terms in the angle controller. Because gyros measure angular velocity, and if you integrate that, then that will give you angular displacement. And then using that value, you would be able to tell like, oh, I want this angular displacement, and my gyro is telling me I have this one right now. So yeah, that would basically just replace looking at the encoder counts of each wheel. It's like, there are ways to like combine, like looking at the wheels and the gyros, like that's a bit complicated. So most people, what they do is like they either look at either one or the other. Either just use the encoders or they use a gyro. Yes.
So I assume the Micromouse is not allowed to communicate with an external computer during the competition?
It's like during the competition, no, but you could just
I
like
mean-
if you want to include like something like say a Bluetooth module, like you just can't use it during the competition, you know.
Yeah, one of another IEEE officers, previous Micromouse lead Bradley, he has like an HC05 Bluetooth module on his, and then from that he can just like control it from his computer, like put in arrow keys and then just like do whatever with it. It's a fun thing to do, but during the competition, no, you cannot. Alright, anything else? Okay, then I'm gonna speed run back to the last slide. Yeah, so what we've been talking about, we're gonna drop the new assignments tonight. Congrats on all you guys. I'm pretty sure we had like 100% completion rate for assignment 1, so thank you guys for getting that in on time. I'm talking about assignment 1A, not 1B. I haven't actually checked that. But
Well,
1A,
it's
you
close
guys are
though.
good.
It's like you guys are doing a good job on getting your things done.
Yeah, we'll get a round of applause for that.
Right.
Okay. So yeah, what we were talking about earlier, assignment 3A, remember those are the team assignments, only one person per team needs to submit that, but basically setting up all of the equations that we've been talking about, the proportional and derivative controllers. Goal number 1, just drive in a straight line, and then after that, we'll learn how to set up the distance controller to like drive a set distance, and then after that, finishing off with our angle controller, like turning a set distance. And then assignment 3B, more Autodesk Eagle, but this time, wait, I didn't update this.
Okay, let's just pretend you do not see that text, but assignment 3B, you'll be using more of Autodesk Eagle, I can tell you that. And instead of adding more to your schematic, you'll actually be designing your PCBs in that. And you'll get to learn like the PCB design side of Eagle. And just kind of just get a feel for it, kind of get used to it, and just kind of lay your things out in a nice board.
Yeah, so the circuit that you guys made, like the schematic that you made in assignment 1B, the voltage regulator circuit, you were actually going to be like using the PCB board layout features of Eagle to like design the PCB board, and then you're not going to order it, but you can see how to order it, and like just like the later half of the PCB design process.
And yeah, like this will be due
yes.
on the 18th. We'll have another work session this Saturday. Just feel free to pop by, drop in, just get your assignments done. or get started on this
Yeah,
assignment.
so that's this Saturday from 12 to 4, IEEE Lab. You all know where that is. Yeah, and then some more of our announcements for this week. Our PCB design workshop that we mentioned last lecture, it got pushed back to next week. They're still figuring out the location, but it should be at 6:30 in person now, I think. Lecture 4, so we originally had it planned for November 15th, Tuesday, but then we realized you guys had a Smallberg midterm, and I know a lot of you guys are in Smallberg, so we just had to push it back to Wednesday, 7 p.m. That's the only time that works for us that week. If you guys can't make it, like, we always have our recordings, but if you can, just like, this will be the last lecture that you need to like actually be able to solve the maze. Like, this will be like the final piece for fall quarter. And then assignment 2A and 2B, we pushed the deadline back to like give you guys a little bit more time to work on that. I don't know what it was before, but now it's due. Now it's due next week, same day as PCB design work. Okay, I'm pretty sure that's a Tuesday.
That's a Tuesday.
We're gonna update the slides
We're
after
gonna
this.
update the slides.
And
Don't worry about
you
it.
also wrote 08 instead of.
Yeah.
Close enough. Like
Man,
08
it's-
works, okay?
It's midterm week. We're all
It's midterm
tired.
week.
Whatever. You guys all did this. You guys are good. And yeah, that's all we got for today. Any more questions? Yeah.
Can we use a different control, like a control computer, or do we have to use the Nucleos?
Oh, you mean when you
fall
make your
or
own?
for winter?
Yes, for fall.
For fall, like, yeah, you'll have to use the nucleus.
Yeah, for fall you will be using the kits we give you, but then in winter,
We have a set microcontroller.
yeah,
the-
but like if you're able to get your own microcontroller, like not through us, that's also fine. But I'll just say for the mice that you make in winter, we're not using the Nucleos. We're using like a tiny microcontroller. That's like, so then you'll have a lot more space to put other stuff on your board.
It's roughly like what, a square of my thumb. To be honest, like it's like that small. So you
Yeah.
guys will have a lot of freedom in terms of like spacing and all that. And it's more robust than like the
Yeah, it's
Nucleo
more robust than
microcontroller.
Nucleos.
So you guys get a little bit more freedom with like in terms of input outputs and just other additional stuff.
Okay, but we do have to use the new one for winter.
Yeah, like it would be nice if you can find a separate microcontroller, but it could be out of like our scope in terms of how to code it. And the other thing is we're still in a chip shortage. It's gonna be hard to find some sometimes.
Yeah, but
That's all good.
I wouldn't worry about that till like I don't know, a month from now.
Yeah, like you guys can worry about that once like you guys start designing it, but we're not there yet.
Yeah. Oh, also, a question. This is like not related to this at all. How many of you guys would be available like Thanksgiving week Monday evening? Or like how many of you would still be around, still in town? Okay,
All
so
right,
a good
cool.
chunk of you.
Because we're actually going to be doing a design related lecture. It's not a lecture required for you to like compete in our fall rack competition, but it'll be a pretty useful lecture when it comes to like designing your mouse for winter, or like you can actually get started on winter break if you'd like. But
Yes, that will be a lecture where we teach you guys like all the different components you can add in winter, and then also we're trying to see like if there's enough interest, we'll try to get pizza for that day,
and then
and free
Like,
free food's nice.
yeah, and just it's gonna be like we have the lecture, we head down to the IEEE lab for some pizza, and then slide into a work session. So you guys.
Or you guys just socialize.
Or you guys can
whatever
just
you want to
socialize,
do.
whatever
But
you want. It's up to you
we
guys.
thought it'd be fun, just like week 9 after midterm, just like hang
Thanksgiving
out.
week, you know?
Yeah, Thanksgiving week. But yeah, all right, that's all we got for today. Thanks for coming, guys.